In this video, we are going to be going over the odd and even trigonometric identities. Some of you may have seen these in your pre-calculus or trigonometry classes. Some of you may not have. In any case, you'll hopefully be able to pick up some valuable information from these videos. So here I have the graph of sine of x. F of x equals sine of x. And I've shown two periods of it. One period is just one unit over which it repeats, like you can see, goes up to -1, back to 0, goes up to 1, down back to 0, down to -1, back up to 0, and the same thing happens indefinitely. And the period over which it repeats is 2 pi. But what we're going to be focusing on here is what is the value of sine of x, sine of -x, relative to sine of x. So let's say we are interested in the sine of pi over 4. Pi over 4 is roughly here. The sine of pi over 4. The sine of pi over 4 is the square root of 2 over 2. Now let's say we're interested in the sine of negative pi over 4. Well, negative pi over 4 is somewhere here. So the sine of negative pi over 4 is negative square root of 2 over 2. And it seems here for every point x, y, you have a point negative x, negative y. So here the sine of pi over 2 is 1, but the sine of negative pi over 2 is -1. The sine of pi is 0, the sine of negative pi is 0. The sine of positive 3 pi over 2 is -1. The sine of negative 3 pi over 2 is positive 1. So it seems like the sine of negative theta is equal to the additive opposite, or minus the sine of theta. So when theta is pi over 4, sine is square root of 2 over 2, but when theta is negative pi over 4, sine is negative square root of 2 over 2. And we showed several other examples of how this works out. Now hopefully you'll remember that the cosecant function, cosecant of theta, is 1 over sine of theta. So this means that these three dots simply means therefore. So the cosecant of negative theta is equal to 1 over the sine of negative theta. Here, negative theta is just another theta. So think of this as, x. Whatever's it, we're saying the cosecant of whatever's in here is 1 over the sine of whatever's in here. And whatever's in here is negative theta in this case. Remember, we just showed that the sine of negative theta is equal to negative sine of theta. We didn't show it in general, but we looked at a few cases and saw that it's pretty reasonable to assume that this is indeed the case, because this sine function just keeps on repeating. So we can rewrite this sine of negative theta as negative sine of theta. And this is the same thing here as having this minus sign out in front. So 1 over negative sine of theta is negative 1 over sine theta. What's 1 over sine theta? It's just cosecant of theta, right? So this is negative cosecant of theta. So cosecant of theta is also negative cosecant of theta. Just as sine of negative theta was negative sine of theta, cosecant of negative theta is negative cosecant of theta. Ignore this drawing of the unit circle for a moment. We'll get back to it later. Now I've drawn the cosine function, and I've drawn two periods of it. One period is just between is one unit in which it repeats. So you can see it going from 0 to 2 pi, goes down from 1 to 0 at pi over 2, then goes down to negative 1 for x equal to pi, and goes up to 0 for x equal to 3 pi over 2, and then up to 1 for x equal to 2 pi. And it repeats in that fashion. And the same deal from x equal to negative 2 pi all the way up to x equal to pi. And here, remember from this unit circle, theta going from 0, this is theta equals 0, and counting towards pi, we are moving counterclockwise along this circle. If we are starting at negative 2 pi, that means we have moved a full circle clockwise, and we are starting at negative 2 pi, and we are continuing forward, so we are going in the counterclockwise direction back to 0, and that would be going from here to here, from x equals negative 2 pi to x equals 0. But more importantly, we are concerned with what is the cosine of negative x relative to the cosine of x, or cosine of theta, negative theta relative to cosine of theta. Well, let's say we're looking at the cosine of pi over 4. Cosine of pi over 4 is the square root of 2 over 2. But what's the cosine of negative pi over 4? Negative pi over 4 is somewhere here. This is negative pi over 2. So I have hatches every, or I've hash marks every pi over 2. So this is negative pi over 2. So around here would be negative pi over 4. And cosine of negative pi over 4 is also equal to square root of 2 over 2. So it seems like cosine of negative theta, or negative x, is equal to cosine of theta, or x. And let's see how that pans out. So the cosine of positive pi is negative 1, but the cosine of negative pi is also negative 1. So in general, the cosine of negative x is equal to the cosine of x. Now hopefully you remember that secant of x is 1 over the cosine of x. And it was defined to be this way, so I could put 3 lines, and this just means is defined as. So then secant of negative x is going to be 1 over cosine of negative x, because this just says that secant of whatever's inside this parentheses, so I could have put a parentheses here, is equal to 1 over cosine of whatever's in this parenthesis. So here negative x happens to be in this parenthesis. But we just said that cosine of negative x is equal to the cosine of x. But what is 1 over the cosine of x? It's just secant of x, right? So just like the cosine of negative x is equal to the cosine of x, secant of negative x is equal to the secant of x. Now going back to sine, we found that the sine of negative theta, or I can rewrite this as x if you want. The sine of negative x is equal to negative sine of x. Okay, but the cosecant, we have here the cosecant of theta. Another way of saying this is the cosecant of negative x is equal to negative cosecant of x. But for cosine of negative x is equal to cosine of x itself, while sine of negative x is equal to negative sine of x. And for secant of negative x is equal to secant of x itself, but for cosecant of negative x is equal to negative cosecant of x. If we look at the graph of sine, it's symmetric about the origin. If you graph cosecant, it's also symmetric about the origin. Cosecant's going to be 1 over sine, so it'll kind of look like this with vertical asymptotes wherever sine is 0. So cosecant will look something like that, like I've drawn there. It'll be equivalent to 1 wherever sine's 1, and wherever sine's 0, it'll have vertical asymptotes, and around those points it'll be tending to positive infinity on one side of it and negative infinity on the other side of it. And you can see that this is also symmetric about the origin. So when you have a function for which functions of the form f of x, where f of negative x equals negative f of x. So when you apply the function to the opposite, the additive opposite or negative of a particular number, you are going to get negative of the function applied to that number, the additive opposite of the function applied to that number. And these types of functions, sine and cosecant are examples, these are called odd functions. And graphically they're symmetric about the origin. Well, cosine, if you look at it, it looks like it's symmetric about the y-axis, right? Looks like if you could kind of flip any chunk of the graph over the y-axis, and it'll really map onto itself. Here, like if you flip this over the y-axis, you'd get a point here on the graph of cosine. If you flip this over the y-axis, you get a point here. And that's the case for all functions that are for which f of negative x equals f of x. So when you apply this cosine to negative pi over 4, you will be getting something equal to cosine of pi over 4. And now the graph of secant, okay, it is going to be 0. It's going to have vertical asymptotes wherever cosine is 0. Remember, it's 1 over cosine. It'll be 1 wherever cosine's 1. So oops. So it basically, it looks like that. This is cosine. This is the secant function. These kind of look like a collection of parabolas here. They're not really parabolas, they just look like that. And you can see that they're symmetric about the y-axis. You take this half of this, what seems to be a parabola, I'm using parabola in quotations, reflected about the y-axis, you'll map it onto itself. And you can take this parabola here, reflected about the y-axis, you'll pretty much map it onto itself as well. Oops, shouldn't be there. And you'd map this onto here. So you have this symmetry about the y-axis. The function evaluated at the opposite of a number is equivalent to the function evaluated at that number, or f of negative x is equivalent to f of x. And we call this function, these types of functions, even functions. And here, the two examples I've shown are cosine of x is an even function, so is secant of x. Okay. Now we're going to look at the graph of tangent of x. Now, what's the deal with tangent of x? Why does it look like this? Well, remember tangent of x equals sine of x over cosine of x. Okay. So you are going to have vertical asymptotes wherever cosine of x is equal to 0. And it's going to be equal to 0. Remember, cosine is the x coordinate here on this unit circle, and is going to be equal to 0 when when you sweep theta like so. This is theta, and theta heads in this direction. When theta is pi over 2, so when theta is pi over 2, cosine is 0. Sweep 180 more degrees when theta is 3 pi over 2. Cosine is also 0, so we have a vertical asymptote. Working in the counterclockwise direction, when theta is negative pi over 2, you have a vertical asymptote. That is the same thing as 3 pi over 2 in the positive direction. And at negative 3 pi over 2, so working clockwise all the way to here, that is the same thing as going counterclockwise in the positive direction, just pi over 2. But at theta equals negative 3 pi over 2, cosine is also 0, so the tangent has a vertical asymptote. And it's going to be 0 wherever sine 0. Sine is 0 at 0. It's 0 at pi. So this is pi here. And heading in the negative direction, it's going to be 0 at negative pi. Okay. And the graph looks like this. In a previous video, I've reasoned out why the graph looks like it does. And really, it boils down to the relative sizes of sine x and cosine of x. When tangent is a really big positive number, what that means is sine of x is going to be very close to 1 and positive, and cosine of x is going to be very close to 0 and positive. Either that or sine of x is going to be very close to negative 1, and cosine of x is going to be very close to 0 but negative. Okay, so very close to pi over 2, you're seeing a huge value for tangent, and the same deal very close to 3 pi over 2, but on the left of it, and also on the left of pi over 2. And the same reasoning can be used to figure out why the rest of the graph looks like it does. But now we're interested in what is the tangent of negative x relative to the tangent of x. This is pi over 2. I have hash marks every pi over 2. So let's say we want to find the tangent of pi over 4. The tangent of pi over 4, well, it's sine of pi over 4 with cosine of pi over 4. Sine and cosine are the same at pi over 4, so their ratio is 1. Tangent of pi over 4 is 1. But what about the tangent of negative pi over 4? Tangent of negative pi over 4. Well, heading pi over 4 in the clockwise or negative direction here, this is negative pi over 4. You can see sine is going to be negative here, but cosine is going to be positive. And they're in magnitude, they're going to be exactly the same. So sine is going to be negative square root of 2 over 2, while cosine is going to be positive square root of 2 over 2. So positive square root over, or negative square root of 2 over 2 divided by positive square root of 2 over 2 is going to give you negative 1. So here it looks as though the tangent of negative x is negative the tangent of x. And that is indeed the case. We have shown one example, but pretty much for any point here, if you flip it around about the origin, not the y-axis, but the origin, you can generate another point on that graph. Okay, like the point generated from flipping about the y-axis of this point on the graph looks like it's about here. If you want to flip something here on the not over the y-axis, around the origin, I should say, looks like it's about here. Flip something here on the graph about the origin, looks like it'll end up somewhere here, and so on. So the tangent of negative x is equal to negative tangent of x. And if you remember from discussion of sine and cosecant, this is an odd function because f of negative x equals negative f of x. Now what about cotangent? What does it deal with cotangent? Well, if you remember, cotangent of x is cosine of x over sine of x. But tangent of x is sine of x over cosine of x. So this cotangent of x, cosine of x over sine of x, this is 1 over sine x over cosine x. So this is 1 over tangent of x. Okay, so bearing that in mind, what is cotangent of negative x? Well, it's going to be 1 over tangent of negative x. But we said tangent of negative x is negative tangent of x. Okay, now I just explained why that was. And so this is the same thing as negative 1 over tangent of x. But remember, 1 over tangent of x is cotangent of x. 1 over tangent of x is cotangent of x. So negative or cotangent of negative x is negative cotangent of x. So just cotangent of negative x is negative cotangent of x. So I'm going to circle all these odd even identities. This is one of the odd. This is the odd even identity for cotangent. It's an odd function. This is the odd even identity for tangent. It is also an odd function. Here is the odd even identity for sine. It is an odd function. Here's the odd even identity for cosecant. It is an odd function. Here's the odd even identity for cosine. It's an even function. And I'm going to rewrite the odd even identity for secant, which is also an even function. And we're going to be using a lot of these in future problems we work and in various proofs, so I thought it may be worthwhile to show them and state them here.